I appreciate the opportunity to present, and it's my pleasure to take part in Virus Bulletin localhost. My name is Dongwook Kim, and I'm going to present with my coworker Sojun Liu. This is my manager Jae Lee, and other coworkers are Byeongjae Kim, Taewoo Lee. We are from South Korea, and we work at the Korea Internet Security Agency (KISA). Also, we belong to KrCERT, so we have been investigating many cyber incidents occurred in Korea. The agenda is as follows. First, I will introduce about risk of supply chain attacks and 5 cases that we have analyzed. This section reviews the supply chain attack hijacked ASUS update file to show you how risky a supply chain attack can be. This slide shows a scenario of the attack against the ASUS. We were able to understand the scenario by analyzing the malware provided by Kaspersky. An attacker compromised an ASUS update server and tampered update program with the malicious update. Then, it infected more than 1 million computers through the automatic update service. Next, the installed malware collects MAC address of the infected devices and check if this machine is target. After that, the attacker distributed the final payload only to devices that have a specific MAC address. The attacker distributed 2 types of tampered update files. Type A runs the shellcode in the modified winMain function. When the modified winMain function is executed, it loads the shellcode in the memory. Type A uses a simple code that terminates itself after only executing the shellcode. On the other hand, Type B runs the shellcode in the modified runtime code. When the modified runtime function is executed, it allocates additional memory space and reads shellcode in the resource area. And then it decrypts the shellcode and loads. The algorithm to decrypt the shellcode is the same one used in PlugX malware. Then the malware checks the MAC address of the infected system to select targets. It installs the additional payload after verification. Researchers at Kaspersky found more than 600 unique MAC addresses in 200 samples used in. They named this attack as Operation ShadowHammer. Kaspersky reported that its solution detected about 57,000 infected PCs, and more than 1 million PCs were probably infected worldwide. Now, I'm going to review the 5 cases of supply chain attacks that we analyzed. This slide shows the timeline of the attacks carried out by the same group. This is case A. The attacker compromised the update server to install a malware on the intranet PCs and leaked personal information. The attacker uploaded the malware to the distribution servers first, and then, if specific IPs of company A requested update, they were redirected to the malware distribution server. As a result, a total of 62 PCs were infected, and the attacker hijacked personal information of 35 million people in Korea. They would have hijacked a certificate and signed it to avoid detection by the security system. The malware downloaded from the update server was the PlugX. PlugX gets the CNC server addresses after decrypting the data. It checks these strings to verify if the decryption is successful. This is one of the features of PlugX. The malware performs malicious behavior, such as controlling databases, so they could hijack personal information using this malware. This slide shows case B. The attacker connected to the build server using account of TeamViewer. We are not sure how they got the account. After that, they modified normal link.exe to generate malicious code. Therefore, some users were infected when requested an update. The first installed malware was PlugX. It allocates several memory spaces and copies malicious modules into each space. Although the behavior of the malware is different from the original PlugX, but we determined it is a variation of PlugX by checking the following features. It gets the config data such as version, CNC address, and checks if this data starts with XXXX. We presume this version just has been updated before conducting the attack. The malware connects to the specific GitHub page or TechNet page, which combines DGA constructing by the attacker, and pushes the specific data to obtain the CNC server address. Due to this, the attacker was able to change CNC server address at any time. After taking control over the server with PlugX, the attacker modified the link.exe used for compilation. When the developer compiles, the source code containing the malicious code is generated. Next, modify the response file to include the object file created by cl.exe in the linking process. Finally, an update file was created in which only malicious code was added from the existing file. These slides show an update file modified by the attacker. This malicious update file can be signed with a normal certificate because it has gone through the process normally. The malware connects to the CNC server using a DGA. The domain is created based on the time of execution. The domain consists of 10 to 15 alphabet characters suffixed by .com. The malware used victim device information as a subdomain. The list of information configured as follows to match the DNS query format. The malware communicates with the attacker using DNS tunneling in the way shown here. It processes the DNS query in a TXT method. TXT method allows attackers to distribute additional data in free form. Then, the attacker decrypts the target's information to select the target and transmits the additional payload with the DNS response packet. The attacker can register the CNC domain at the desired time and communicate with the infected devices. This is because DGA is created based on the time that the malicious code is currently running. In this way, it is very difficult to detect because the connection is made by activating a specific domain only at a specific time. Now, I'm going to introduce another presenter, Sojun Ryu, to take over this presentation.
Hi, I'm Sojun Ryu and going to continue the presentation. This is about case C. We could confirm this attack as suspicious access to an abnormal URL has been identified on a customer PC using this program. The attacker logged into the remote control server with a test account used by company C. Then the attacker could move to an intranet through the remote control server and change the proxy settings of the update server to distribute the malware. We confirm the attacker also used PlugX. This malware finds a specific character string to parse the CNC server address in the same way as the previously explained at the case B. Then it controls the system and steals information using commands. And finally, the attacker succeeded to distribute the malware signed with normal sys certificate using the update server. This capture shows the certificate has expired, but it was buried at the time of analysis. They used the PlugX path of Nginx to select the target pieces for the attack. Using this function, the attacker can redirect to a malicious distribution site when customer IP in the PlugX path trying to update software. We found from firewall log and settings log that 2 customers tried to connect to the malware distribution site. Detecting this attack is very difficult because they used the normal function of Nginx and only targeted specific companies. The customer IP in the proxy path was redirected to the malware distribution server when trying to update software. Like this, the attacker understood the update process in company C and then distributed the malware in the same way as the regular update process. The attacker first distributed the modified update.ini file and configured it to download additional malwares through it. Additional malwares were a log file containing the shellcode and a DLL file that loaded the log file. The attacker set it to not work after the months in which the attack was attempted. Company D is infected with malware due to supply chain attack using Company C's program. The employee of Company D tried to update of Company C's program. As a result, the employee's PC was infected with a malware by downloading and running a tempered update file. The employee's PC was on a network without network separation and strict access control, so the attacker was able to move the developer's PC. Then the attacker could remotely control the developer's PC, so logged into the SVN and stored the source code of Company D. The final malware executed from a malicious update file was a variant of the 9002 rat. This malware was first found in Operation Aurora in 2009 and is known to be the malware used by Group APT17. And we found an attacker's mistake in the malware. The 2012 January 11th version value is used for the first connection, but the 2018 July 17th version value is used for all other communication. This seems to be accidentally missing when updating the existing version of the malware. And the attacker also used the same PlugX malware used in the Company C. The version was 2012 July 12th. We think the attacker mainly used the PlugX malware than 9002 malware, because they installed PlugX to victims of this attack after controlling infected devices successfully. Perhaps it is dangerous for them to continue to use tempered malicious update files, so they may have used additional PlugX or simply to maintain persistence. The attacker modified some command files over Linux server to hide their mark. They modified nested, PS, etc. So the engineers couldn't find unusual behaviors, as command output shows the normal result excludes the attackers' IP. This is about case E. The update server was compromised by the attacker. The attacker logged into the update server's webpage with an administrator account hijacked in advance. Then the attacker unloaded the web shell. The attacker gained access to the server through the unloaded web shell and succeeded in elevating it to the root with some vulnerability. Then the attacker tampered PAM unix.so file to collect internal account information. Thanks to the immediate report of the victim, we were able to block the attack before the attack was fully completed. The attacker modified PAM unix.so, which was the library file of the PAM module that was the authority framework used by Linux. This file performs functions like inspecting the validity of the user password and whether to allow service access. The tempered file operates when some users connect to the update server using like login, SSH, sudo su. As a result, the ID and password were recorded, and the attacker was able to collect these accounts. The attacker modified the command file in the same way as case D. We have been continuously analyzing supply chain attacks occurred in South Korea. We have also gathered information about CCleaner and ASUS incidents that took place overseas in an open report. As this table shows, each supply chain attacks had 2 or more common factors. We summarized these attacks in 6 characteristics. Most supply chain attacks distribute a malware to infect only the targets they wanted. Moreover, PlugX and code tampering techniques were often used. In conclusion, we presume that the attack group performed supply chain attacks against Korean companies and the group performed supply chain attacks against ASUS and CCleaner would be the same. The attacker used PlugX in most supply chain attacks. PlugX is used by many Chinese-based APT groups, including the BARIUM APT group. We obtained various versions of PlugX through analysis. The attacker especially updated the version for version control just before installing the malware. All malwares were created immediately after the set version date. As such, we presume the attacker had experience using or developing PlugX time malware for a long time. The attacker used 2 strategies for the supply chain attack: penetration into the development environment and penetration into the update server. Both strategies require advanced techniques for a successful attack. It's the optimal way to distribute a large volume of malware secretly during a short period. The strategies through penetration of the update server can distribute malware by changing only some settings without penetrating the development environment. The strategies through penetration into the software development environment can intervene in the compile process. So the attacker can try more sophisticated attacks. However, this is more difficult to detect because it can get deeply involved in the source code. Both can be deployed in large quantities according to the attacker's strategy, or it can be done by designating only a specific PC. And it is more difficult to penetrate the software development environment and requires sophisticated technology. More detailed analysis and countermeasures can be found in this report. Thank you for watching our presentation.